Good morning, everyone. Thank you for joining us. I'm Aishu Venkat, and it is my pleasure to welcome you to the webinar on the significance of measuring IGF-1 in diagnosing growth hormone disorders. This webinar is hosted by the Euroimmune Academy in the United States. Following the presentations, we will open the webinar up for a Q&A session with our speakers. If you have any questions for them, please type them in the chat box seen on your screen. If you're interested in claiming PACE credits for this webinar, it is important you log on individually and stay for the entire duration of the webinar. After the webinar, you will also receive an email on how to claim your PACE credits certificates. Without further ado, it is my pleasure to introduce you to our first speaker, Dr. Martin Bidlingmaier. Dr. Bidlingmaier is the head of endocrine laboratories and leads the neuroendocrine research group at the Department of Internal Medicine, Ludwig Maximilians University in Munich, Germany. His research interests include the development and validation of laboratory methods for pituitary and adrenal hormones, clinical applications and biochemical monitoring of growth hormone, and endocrine aspects of doping in sports. Dr. Bidlingmaier has authored over 340 articles in peer-reviewed journals that has been cited over 13,000 times. He also serves as an editor of the journal Pituitary and is a member of editorial boards of several other journals. In 2022, he published a key publication that analyzed the distribution of IGF-1 levels in the United States and Europe, including an extremely large cohort of over 1.4 million subjects. Dr. Bidlingmaier, we are all looking forward to hearing more about this study and others during your presentation. Now, I will pass it over to you to begin your presentation.
Good morning, everybody. I'm Martin Bidlingmaier from Munich University, and I'm here to discuss with you how to measure growth hormone and IGF-1 in children and adults, and about its clinical significance and analytical challenges. These are my disclosures. And this is our agenda for today. I start with a few informations on the background of IGF axis physiology. I'm discussing with you clinical features of growth hormone-related disorders in children and adults. I'm referring to guidelines for diagnosis. And then I switch to discuss analytical challenges when measuring growth hormone and IGF-1. And finally, I will present some data on diagnostic cutoffs and reference intervals and discuss how important these are. Let's start with the physiology of the growth hormone IGF axis. Growth hormone is a peptide hormone secreted by the pituitary gland. And in the human body, growth hormone secretion is mainly regulated by positive and negative factors, which include, most importantly, growth hormone releasing hormone, which comes from the hypothalamus, and as an inhibitor, we have somatostatin, which also mainly comes from the hypothalamus, as far as it's important for growth hormone secretion. It's also produced in other parts of the body, but to regulate the pituitary, hypothalamic somatostatin is most important. Only a few years ago, it was discovered that another hormone coming from the stomach, which is named ghrelin, is also an important positive regulator of pituitary growth hormone secretion. Once in circulation, growth hormone itself has effects in many organs. However, the main target is the liver. And in the liver, upon stimulation by growth hormone, IGF-1 is produced. IGF-1 is the factor which translates into effects, many of the effects of growth hormone. in peripheral tissues. And the final step in the feedback loop is that in healthy subjects, IGF-1 itself inhibits pituitary growth hormone secretion. So what are the effects of growth hormone? I think the most prominent effect, or the most well-known effect, is the effect on growth, on bone, on longitudinal growth of bones. In addition to bones, where it's mainly important in children for the length of the bones, we have effects on connective tissues and cartilage, but at the same time, we have important effects on muscle mass and adipose tissue. And these effects last for the whole lifespan. So it's not just a hormone which is important to growing kids. It's important also in adults. In addition to these most prominent effects, growth hormone is an important regulator of glucose metabolism. It has effects on the kidney, the heart, and the immune system. So overall, it's a pleiotropic hormone which affects a lot of our health. Growth hormone-related disorders have a different clinical appearance in children and in adults. The first condition is too little growth hormone. Too little growth hormone in childhood is almost exclusively by genetic causes. So we have mutations in transcription factors or in the DNA for receptors, growth hormone receptors. Sometimes we also have tumors and trauma, which damages the pituitary gland. And in many of the patients, we also have the situation that we cannot clarify the cause of the deficiency. So this is the group of idiopathic growth hormone deficient children. So we have childhood onset growth hormone deficiency, and the frequency varies in the literature. It's among 1 in 5,000 to 1 in 30,000 kids. In adults, the number is about 1 in 10,000, and the reason to have growth hormone deficiency in adulthood is either because it already was there in childhood, so childhood onset growth hormone deficiency, or because of a trauma or tumors damaging the pituitary gland. In children, we have a clear oxalogic measure of growth hormone effects, which is height. Height and height velocity are grossly reduced in growth hormone deficient children. And here you see an example of kids which are clearly too short for the age. In adults, it's much more difficult to correlate a specific clinical symptom to growth hormone deficiency. We have mainly adiposity, we have fatigue, weakness, we have a lot of symptoms which are not as clear as in children, where we simply have the reduced height velocity and the reduced size. But if growth hormone deficiency starts in adulthood, the patient already has reached his final height. So this is not helpful. The main causes of growth hormone deficiency in adults are nicely summarized in this slide from a recent publication in the New England Journal of Medicine. So we have the group of diseases affecting the health of the brain. We have important effects on growth hormone secretion of obesity. We have immunological effects like hypophysitis. We have hormones which reduce growth hormone secretion. We can see vascular damage in some patients. And we also have the large group of compressive masses which damage the pituitary gland, so mainly brain tumors or metastasis. I want to highlight two factors which are more common maybe than others. The one is head trauma, which occurs often in traffic accidents and other conditions. So this is a potential cause of growth hormone deficiency. And we have, in recent years, more cases where immunotherapy for cancers affects the pituitary gland, leads to a hypophysitis, and this reduces growth hormone secretion. Another aspect which we should not underestimate in its importance is obesity. Obesity, free fatty acids in circulation, reduce growth hormone secretion. So growth hormone deficiency can be the cause of nutritional factors. These pictures show two historic patients which got growth hormone excess during childhood. That's an extremely rare disorder, 1 in 200,000 subjects or kids. The disease is called gigantism. The cause of the disease is a pituitary adenoma, which secretes too much growth hormone. And as long as there is longitudinal growth, it's grossly stimulated by growth hormone, and therefore these patients can have excessive height. Today, we do not see very often such cases any longer because the disease is detected much earlier. Most of the patients with growth hormone excess, with too much growth hormone we are seeing today, are adult onset patients which have a disease called acromegaly, which comes from GH producing pituitary adenomas in most cases. Excess secretion of the hypothalamic GHRH is a very, very rare thing. And in our patients, our adult patients, we see a typical clinical image where parts of the body are growing which still can grow. So we have enlarged chin and nose and ears, and we have swelling of the hands. The feet are growing, so patients complain about shoes not fitting any longer. The ring size increases. And unfortunately, it's not only the visible symptoms, but we also have organomegaly and cardiomegaly. We have impaired glucose metabolism, and this is a very severe disease which requires appropriate treatment. It develops very slowly, so early diagnosis remains a challenge. The diagnosis of these disorders, and particularly the biochemical diagnosis of growth hormone-related disorders, is very simple in theory. We can have low growth hormone and low IGF-1 in growth hormone deficiency, and we have grossly elevated growth hormone and IGF-1 in acromegaly. The first complication is that we also can have a situation of so-called growth hormone resistance, where we have a defect of the growth hormone receptor. So IGF-1 is very low because growth hormone cannot stimulate IGF-1. However, the negative feedback on the pituitary is impaired. So the pituitary tries to compensate and secretes more growth hormone. However, we have more complications. We have the situation that we have a pulsatile secretion. I have shown this before. So a random growth hormone value is not very helpful. With very, very few exceptions, growth hormone stimulation tests are required to diagnose growth hormone deficiency, and a suppression test is required to diagnose growth hormone excess. Because just by having a high or a low random growth hormone, we do not know anything about the status of the patient. In children, there is a little bit of heterogeneity between countries and guidelines on how to best stimulate growth hormone secretion for these tests. This is a recent publication comparing the recommendations in various national guidelines. And you can see that in some countries, this is Spain, clonidine test and insulin hypoglycemia are done in children, while in others, like for example in Italy, glucagon, arginine, or GHRH arginine combined tests are more popular. In the US, arginine alone or clonidine tests seem to be the most popular ones. To further complicate the situation, there's also no agreement on whether or not so-called priming should be done before testing. Priming means that you induce a defined pubertal state by giving sex hormones to the kids before testing. In some countries, this is not recommended. In others, including the US and Great Britain, this, and also here in Germany, this is a very common procedure. In addition to the differences in recommending different stimulation tests, there's also discrepancy between the recommendations as to the question whom to test at all. In some countries, -2 SD in height is a reason to test. In others, there is more flexibility, even if you are below target, which can be calculated from your parents' height. It can be a problem. And in addition, height velocity is also a parameter which can be used to identify subjects which need testing. However, the recommendations are also different between different countries. In adults, there is a more homogeneous picture. We have 4 tests today which are used in many countries, and the decision which test to use is mostly made by availability of the agents or by experience of the center doing the tests. The gold standard still is insulin tolerance tests, where you give a bolus of insulin to induce hypoglycemia. This is not a side effect, it's what you intend to get, hypoglycemia, because that's the stimulus for the pituitary to secrete growth hormone. However, this makes the test potentially dangerous, and of course, there are contraindications. A more convenient test for most patients would be GHRH arginine, where you give a bolus of GHRH together with an infusion of arginine. However, in some countries, GHRH is not available, and I think this includes the US. Another test is glucagon, where you inject glucagon into the muscle. You get a sufficient stimulation of growth hormone. However, the test can be associated with side effects. A more convenient setting, because it can be given orally, is the more recent development of massimorelin. It's a ghrelin receptor agonist, which stimulates growth hormone secretion. And the contraindication is concomitant use of drugs known to prolong the QT interval, but otherwise, a lot of patients like this convenient method to do the growth hormone stimulation test by an oral solution. Why do we have to measure both growth hormone and IGF-1? What is the difference in the clinical meaning of a growth hormone concentration and an IGF-1 concentration? So if we look at the whole picture. We have the growth hormone coming from the pituitary, binding to its receptor in periphery, inducing the signal transduction cascade, and then finally leading to the secretion of IGF-1. If we take a blood sample to measure growth hormone, we have a clear focus on pituitary growth hormone secretion. So we get an understanding of the pituitary's ability to secrete, to make and to secrete growth hormone. In contrast, if we take a blood sample to measure IGF-1, we have a focus on the GH effects in peripheral tissues. We are more looking at growth hormone sensitivity. Not surprising, there is some correlation between the peak growth hormone we can see in a stimulation test and IGF-1. But on the other hand, the correlation is modest only. So it's very difficult to make a prediction from an IGF-1 result about the growth hormone secretory capacity of the pituitary. And this is true both in adults and in kids. In addition, IGF-1 is a factor which is secreted in an age-dependent manner. We have higher IGF-1 at younger ages and lower IGF-1 at old age. And these bars show the reference interval used in this study, and the dots are IGF-1 levels in growth hormone deficient patients, panhypopituitary patients, which do not have growth hormone secretion. And as you can see, while in the younger ones, a low IGF-1 might have some predictive value, it's unlikely to identify growth hormone deficiency in the older subjects just by measuring IGF-1. The older the growth hormone deficient patient, the more likely the IGF-1 remains normal, just because in the normal population, IGF-1 also goes down with advanced age. Furthermore, to fully understand the complex meaning of IGF-1 concentrations, we have to keep in mind that there are a number of clinical conditions which can reduce IGF-1 but not affect growth hormones. So these patients can have low IGF-1 but completely normal growth hormone secretion. And some important conditions to keep in mind is malnutrition, malabsorption, liver insufficiency, any severe illness, of course, but also diabetes mellitus can be associated with decreased IGF-1. So IGF-1 alone might not be sufficient to diagnose growth hormone deficiency, particularly in adults where we do not have the clear sign of reduced height or height velocity. If you look at the guidelines, and I just show the most recent ones published by the respective scientific societies, if you look at the guidelines on how to diagnose growth hormone deficiency, there are some differences between childhood and adulthood. This is the guideline published by Ada Grimberg and colleagues from the Pediatric Endocrine Society in the USA. And I don't go through all details, but I just highlight some of the key statements. So the first one is oxalogic assessment is very important. We should never rely only on biochemistry. The second aspect is that a GH provocative test is important to confirm the diagnosis. There are very, very few conditions where it can be skipped, and they are clearly mentioned in this guideline. For example, if we have the oxalogical criteria, if we have an organic defect of the hypothalamic or pituitary region, and we have a deficiency of at least one additional pituitary hormone, there's a very high pre-test probability for growth hormone deficiency, so it might be skipped if IGF-1 is very low. But these are really few exceptions. The provocative test remains very important. Another important point, particularly from the laboratory's perspective, is that all the guidelines always have a statement that growth hormone and also IGF-1 should be measured with assays adhering to quality criteria from guidelines. And I'm talking about this in a minute. And IGF-1, according to this guideline, is then mainly used to monitor treatment efficacy and adherence. The corresponding guidelines in adults, and this is the one from 2019 from the AACE, makes similar statements, but slightly different because we are talking about adults. So the first statement is random serum growth hormone or IGF-1 levels cannot be used alone to make the diagnosis. That's very important to emphasize because sometimes patients get an IGF-1 result measured for unspecific reasons, and this is a little low, and then the patients are very much concerned. However, I have shown you the biological variability, and it's clear for all the guidelines we cannot base our diagnosis just on a random measurement of growth hormone or IGF-1. So even in adults, growth hormone stimulation tests should be performed to confirm the diagnosis, again with very, very few exceptions. I have shown you the 4 most frequently used stimulation tests, but an important statement in this guideline is that we need test and assay specific cutoffs. And we need to pay attention to confounders, to potential confounders of the growth hormone secretion or the IGF-1 concentration. One important is body mass index or adiposity. The final guideline I quickly want to mention is the one on acromegaly. There's an Endocrine Society clinical practice guideline, and in contrast to growth hormone deficiency, here measurement of IGF-1 is the first recommended tests. And if IGF-1 is elevated, then we can do the confirmation of diagnosis by measuring growth hormone during an oral glucose tolerance test. The next step would be imaging study to see if there's a tumor in the pituitary region. And then during treatment, so after surgery or medical treatment, we are measuring IGF-1 concentrations, and only in some patients reassessing growth hormone suppression during oral glucose load can provide additional information and might be of interest. But the adjustment of treatment, dosing, and so on is mostly based on measuring IGF-1 concentrations in growth hormone excess. So when we have now heard how important the concentrations are from a clinician's perspective, it's time to look a little bit into how to measure growth hormone and IGF-1 and which challenges are associated with the measurement. There was a conference almost 15 years ago defining key criteria for assay quality. And in this consensus statement, there were 4 most important points. The one at that time, very important. Today, most assays have switched. At that time, it was important to emphasize that assays should be calibrated against defined recombinant material. We have an international reference preparation for growth hormone and one for IGF-1 of recombinant origin, and these preparations should be used. The second important statement was that it's important that the specificity of the growth hormone assays is known, and those assays should be preferred which specifically measure the 22 kilodalton isoform. I come back to this point later. A third important aspect is that long-term stability of the assay performance must be ensured through longitudinal quality assessment, quality control. This is important because we are talking about a chronic disease or chronic diseases, and our patients are monitored over years. So the stability of the measurements is of utmost importance. And the fourth point is, because of the known differences in assays, I will show you some examples, it's important to have method-specific, assay-specific cutoffs and reference intervals of sufficient quality available for each assay. Some words on the growth hormone assays. And the first message is that growth hormone assays from different manufacturers or different labs can give very different results. This is the presentation of the data from an external quality assessment scheme where all the participating laboratories got 2 samples, A and B, and had to measure growth hormone concentration. As you can see, in one and the same sample, you can see every concentration between 3 and 12 nanogram reported by different labs and different assays. If we go into more detail, it's obvious that some manufacturers have assays which give lower readings, and other manufacturers have assays which give much higher readings. So if we think about the diagnostic process, where we do a stimulation test, and in some guidelines we have the indication that above 7 nanogram excludes growth hormone deficiency, we have to question if the choice of the assay or the lab makes the diagnosis, because it seems a little bit random if your patient sample ends up in a laboratory generally measuring higher because the assay measures higher. You will get a different patient's population compared to sending your samples to a lab which uses an assay which generally measures lower. An important improvement was the harmonization of the calibrators. Here, this is the situation before the harmonization, where we had more than 30% variability between the labs. And this is the situation in 2017, after most assay manufacturers had adopted the recombinant calibrators. So we have less variability today. However, there's still variability between the different assays. And now the question is, why is this the case? So one important thing to keep in mind is that growth hormone, pituitary-derived growth hormone, is not a very well-defined substance. It is a mixture of molecular isoforms. We have most of the growth hormone being the 22 kilodalton isoform. However, this is only about 50%. We have other forms, smaller forms. We also have fragments. We have dimers, multimers. So it's a crude mixture of growth hormone isoforms. In contrast, the recombinant growth hormone, which is used for treatment, but also for calibration of the assays, is monomeric growth hormone only. This study investigated the abundance of the different isoforms in serum samples, and the key message is growth hormone is not one defined substance, it's a mixture of isoforms. And if you look into the informations from IFUs and also from publications, you see that there is variability between the cross-reactivity seen by different assays. And it's particularly important to know if your assay cross-reacts with the 20 kilodalton isoform with a placental growth hormone or the human placental lactogen, which are secreted during pregnancy. And also, it is important to know whether your assay cross-reacts with pegvisomant, which is a medication used in treatment of growth hormone excess, acromegaly. Some assays have a positive bias when the patient is treated with this drug. Some assays have a negative bias when the patient is treated with this drug. So it's important to know about specificity and potential interference. Unfortunately, the situation of agreement between methods is not much better for the IGF-1 assays. This is the same exercise from an external quality assessment scheme. We have all concentrations reported between 200 and 1000 nanogram in one and the same sample by the different laboratories. And again, if we look at the different kit manufacturers or assay manufacturers, we see that there are assays giving lower readings and assays giving higher readings. So when we see this, when we see that the concentrations reported highly depend on the assay or the lab, the question is, why is it so difficult to measure IGF-1 correctly? There is one specific difficulty with IGF-1 assays, which is related to the binding proteins. To make it more complex, IGF-1 has not only one binding protein in circulation, but two. One is IGF-BP3 and the other is ALS, acid labile subunit. And we have this ternary complex which prolongs half-life of IGF-1 and regulates its ability to bind to the receptor. However, it also makes it invisible, or it makes it more difficult to measure the IGF-1 concentration with no interference from binding proteins. A commonly employed method is acidification, so the complex falls apart. Then there is direct measurement of IGF-1. And while this sounds like a convincing concept in theory, in reality, there's good data demonstrating that we have a problem if we just follow this procedure. And this is because there is insufficient removal from binding proteins and reaggregation. So the gold standard method, which prevents reaggregation and allows accessibility of IGF-1 for the antibodies used in the assay, is IGF-2 displacement. This method starts again with acidification, so the complex falls apart, but then an excess of IGF-2 is added, which blocks the binding proteins. And this excess IGF-2, of course, is a little bit expensive for the assay manufacturers, so it's very important to understand if this method is used and if sufficient amounts of IGF-2 are added, because only when we have sufficient blockade of binding proteins, we can do a very good assessment of the IGF-1 concentration in a sample. More recently, mass spectrometry became available for IGF-1, and some laboratories, particularly in the US, are following this approach. It's an interesting technique. The first thing we need to understand is that it's not the mass spectrometry. There are different approaches, and without going into too much details, there's a so-called top-down approach and a bottom-up approach. The latter being more time-consuming and complicated because we start with digesting the molecules and then analyzing fragments. But this more complex approach also seems to have some advantages in terms of accuracy. So first message is mass spec per se does not tell you a lot. There are many different assays on the market, and there are a few studies comparing the performance of different assays in different labs. Without going into much detail, the key message is if you look at the imprecision of quantification, it is very similar to that seen with the good immunoassays. So for the time being, there is no reason to believe that just by switching to mass spectrometry, you get rid of all the problems associated with IGF-1 measurements. It can be a good method if you have a good lab and good reference intervals, but at the same time, it would be misleading to assume that just because using mass spec, the results are much more reliable. We did this study to analyze differences in the distribution of IGF-1 between European and US populations. We analyzed all samples by the same IDS assay, and we did 3 comparisons. First, we had my published reference intervals from the 15,000 subjects. Then we had about 60,000 samples from European laboratories measured by the same assay. And then we had about 1.4 million, more than about 1.5 million samples from the US. And in this study, we made the interesting observation that for the European sample sets, the original reference intervals based on 15,000 were almost superimposable to the reference intervals calculated from the much larger population of subjects analyzed from the European laboratories. So the original reference intervals were perfectly fine to analyze, at least in adulthood. In kids, of course, it's a little bit different because of the effect of chronological age, but in adults, it was almost perfect agreement. In contrast, when we analyzed the original reference intervals and the reference intervals from the 60,000 European subjects to the 1.5 million American subjects, we made the interesting observation that while the lower limit of the reference intervals is almost identical between Europe and the US, the upper limit should be 15 to 20% higher in the US population. So what is the take-home message? You can use, with this specific assay, you can use reference intervals specific for the US population. You can take these into account. It's particularly important at the upper end of the reference interval. 15 to 20% might not be big enough difference to miss a diagnosis of acromegaly. Patients with overt acromegaly have extremely elevated IGF-1. However, if we treat those patients, the difference of 20% at the higher end of the upper end of the reference interval might become important. So to summarize the 2 parts of my talk, I have a few take-home messages from a clinical point of view. First thing is growth hormone-related disorders are rare diseases, but keep in mind it can affect both children and adults. The name growth hormone is not chosen very well, I think, because growth hormone remains important for human physiology throughout life. So it's not just a kid's hormone, it's a pleiotropic hormone with many functions throughout life. Both too little but also too much growth hormone can cause diseases. So no way to say give growth hormone and everything will be fine. In growing children, we have the advantage that we have the auxologic assessment of height and height velocity, which gives us key information. In adults, the symptoms of growth hormone deficiency are less specific and can develop over years. The same applies to growth hormone excess. So in both conditions, we can have delayed diagnosis. The diagnosis of growth hormone related diseases in clinical practice must follow established guidelines, and these guidelines include the measurement of both growth hormone and IGF-1. For growth hormone, it's a dynamic test in most conditions, which is required, while for IGF-1, we can use determinations at any time point because it's more stable. However, it still has about 30% biological variability within a subject. So a single IGF-1 value does not tell us enough in most conditions. Other biological factors to keep in mind are age, pubertal stage, nutritional status, estrogen use. Of course, I showed you that females require more growth hormone to get the same IGF-1. And these biological confounders must be taken into account when make an interpretation of lab results. My take-home message from the laboratory's perspective are we have to be aware that growth hormone and IGF-1 assays, and perhaps also the labs performing those assays, can differ in terms of quality and also in terms of concentrations reported, and the results can be very different when sending one and the same sample to different laboratories. All the guidelines recommend the use of assays which adhere to established quality criteria. I mentioned those from the consensus statement. Binding protein interference for IGF-1, difference in calibrators and in the antibodies used, and lot-to-lot variability of the assay reagents are common problems. The clinical utility of growth hormone and IGF-1 measurements strongly depend on the quality of the studies which define diagnostic cutoffs and reference intervals. And I believe that this is one of the most important points to keep in mind. If we just take any numbers published 20 years ago in a textbook of endocrinology, we most likely do not have the appropriate numbers for today's assays used in a specific laboratory. As I have shown you, diagnostic cutoffs must be established specifically for each assay and for each diagnostic test, and must take into account biological confounders. For IGF-1 concentrations, I think many clinicians want to see standard deviation scores, so the lab should be prepared to calculate them, which is possible only if the respective information for this particular assay is published in the reference interval publication. And the reference intervals ideally should come from an appropriate background population. And I think cohort size, statistical model, but also the geographical region of the study and so on can have an important impact on the quality of reference intervals. So laboratories should be aware about the source of their reference intervals. This was a long presentation. I hope it was of interest for you. I thank you for your attention. And of course, I'm happy to answer specific questions in the Q&A session to follow. I'm also providing my email address, so please do not hesitate to send an email if you have a particular question. Thank you very much again for your attention.
Dr. Bidlingmaier, thank you so much for that wonderful presentation on the significance of measuring IGF-1 in growth hormone disorders. Our next speaker is Dr. Jenny Manolopoulou. She's currently the Senior Global Product Manager at IDS, where she manages the growth, endocrine hypertension, and adrenaline function panels for the last 12 years. She completed her PhD from Ludwig Maximilians University, where she studied endocrine hypertension, adrenaline steroids, and the development of a saliva-based aldosterone assay. In 2004, she was involved in the detection of recombinant growth hormone abuse by athletes participating at the Olympic Games held in Athens. She has authored several key scientific publications in peer-reviewed journals in the field of endocrine disorders using automated solutions. Now, I would like to welcome Dr. Manolopoulou to begin her presentation.
Good morning, and thank you for joining me today. So today, I'd like to talk you through a few of the publications which we've also heard about in Dr. Bidlingmaier's talk, really to focus on the key technical and clinical characteristics of the growth panel assays, which are used in this field of endocrinology of growth disorders. So the IDS growth panel of automated chemiluminescence immunoassays includes the human growth hormone assay, the insulin-like growth factor 1, the IGF-1 assay, and the insulin-like growth factor binding protein 3, the IGF-1 assay. So these assays are 510(k) exempt in the US, and they are CE marked for clinical routine use in the EU. As we heard from Dr. Bidlingmaier in the previous talk, a few years ago, there was a consensus workshop organized by the Growth Hormone Research Society, really discussing the growth hormone and IGF-1 assays and really the key technical and clinical aspects which should be met by assays measuring these hormones in order to help clinicians in the standardization and really the long-term clinical use of these assays in routine. So following to this consensus statement, the IDS growth panel was available on the market, and with it came really a few key original publications which described the key characteristics of these assays and the clinical reference intervals which come with these. So I wanted to talk you through a little bit, just some highlights from these key original publications. And for the growth hormone assay, our publication in 2012 really highlighted the assay characteristics, including the monoclonal antibody epitopes and excellent specificity of this assay. For the IGF-1 and the IGF-BP3 assay, the two key publications in JCM in 2014 by Dr. Bidlingmaier and Dr. Friedrich really support the assay characteristics and show the key technical aspects, in addition to the specific reference intervals, which we heard a lot about from Dr. Bidlingmaier in the previous talk. More recently, another publication last year on the IGF-1 assay and the US-specific reference intervals was published, which, in addition to these specific population reference intervals, really highlights the long-term stability of the IGF-1 assay from IDS, which is a really key technical aspect, because we heard from Dr. Bidlingmaier that these diseases are long-term, and this is really a key factor which is highlighted by the consensus statement of the Growth Hormone Research Society, but also by many clinicians. These key publications that you see here, along with many others which have been published using the growth panel assays, really make the IDS growth panel the most transparent and extensively published set of assays in the field of growth disorders. So I wanted to take you through a few of the key points just from each of these publications to highlight the important parts. From our clinical chemistry paper of 2012, you can really see there that the growth hormone assay complies to the Growth Hormone Research Society consensus statement. And this publication supports these unique characteristics, not only the monoclonal antibody epitopes and the excellent specificity of this assay, but it also highlights how this assay can uniquely be used to measure growth hormone levels during growth hormone analog treatments like pegvisomant, but also during pregnancy. This publication also was the first one to show for this assay the clinical cutoffs used for the oral glucose tolerance test, which is one of the tests used in acromegaly testing, as we heard from Dr. Bidlingmaier as well. So just to show you a few of the key points from the consensus guidelines, we can really see that the important technical factors which are key in understanding and getting them right for the growth hormone assays. The first of these is to be calibrated to the international standard by the WHO, which is the 98574. In the attempt really to harmonize standardization of all growth hormone assays on the market. In addition to this, growth hormone assays should measure only the 22 kilodalton form of growth hormone. Assays should have a good functional sensitivity down to 0.05 micrograms per liter in order to adequately and accurately measure low levels of growth hormone, such as those which are present during the suppression tests. In addition, growth hormone assays should define their cross-reactivity to 20 kilodalton growth hormone and placental GH. We should define our binding protein interference. We should define interference to the drugs such as pegvisomant, and of course also report results in mass units, towards the harmonization of oral growth hormone assays. These are the key consensus requirements outlined in the guideline, and these are all adhered to by the IDS growth hormone assay. In the more recent IGF-1 publication, which I told you about in the beginning of the talk, last year in the Journal of the Endocrine Society, which describes the differences in the distribution of IGF-1 concentrations between European and US populations. This is really an important publication because it describes the establishment of these reference intervals in a uniquely large cohort of 1.4 million samples, because it was carried out in collaboration with a large reference laboratory in the United States, which is a nationwide lab and uses this IGF-1 assay. And really in this publication, we can see that the differences between observed in the upper limit of normal of IGF-1 values in the US population are highlighted. The observation of these differences in the upper limit of normal led to these US-specific reference intervals, which better reflect now the distribution of IGF-1 levels in the US population. Very importantly, this publication really demonstrates the long-term stability of the IGF-1 assay, which is extremely important for these kind of measurements of this hormone. And this was really carried out by a continuous cross-correlation study over 7 years with data of 20 parallel assessments over these years and more than 200 samples included in the different studies. So this highlights US reference population, but also really the long-term stability of the IGF-1 assay across multiple lots of reagents. I wanted then to to talk to you a little bit about some key publications in terms of the clinical aspects of growth hormone and IGF-1 testing, which you should be aware of, which are key publications for clinical routine use. So starting with growth hormone, really the major tests which we are faced with are in acromegaly testing, the suppression test, which is commonly the oral glucose load, the oral glucose tolerance test. And here we have a key publication of 2019 in the European Journal of Endocrinology, where we actually have cutoffs for growth hormone during this test, which are stratified according to BMI, which we've heard from Dr. Bidlingmaier is a key consideration point when testing for growth hormone levels. In addition, in growth hormone deficiency, we have a lot of the key stimulation test cutoffs already published with the IDS growth hormone assay. You can see here on the left the different tests which are commonly performed for growth hormone deficiency, the insulin tolerance test, the growth hormone releasing hormone arginine test, and several and extensive cutoffs published for these tests. You see here on the right the different publications, and these include studies carried out in adults, also specific levels for children for the insulin tolerance test. In the GHRH arginine test, we have really the cutoffs stratified again by BMI and individually by sex. So in these extensive subgroups published in this paper in 2017. And also more recently, we have the cutoff published in adults cohort for the massimorelin stimulation test. So these are all specific diagnostic cutoffs which have been published for all these dynamic tests and include important considerations of BMI and age. In terms of IGF-1, the important points are really about the establishment of robust reference intervals, as we heard extensively from Dr. Bidlingmaier in the previous presentation. I just wanted to draw your attention to the fact that the consensus requirements really call for the normative data to be specifically characterized in certain terms, including a random selection for all ages. And we have published for the IGF-1 assay in a cohort of over 15,000 subjects. This was a multi-center study, and really the ages are extensive from newborns from 0 to 94 years of age are included. The reference intervals must report SD scores, and we have a specific LMS method which is used to calculate SD scores, which is described in detail in the publication. Reference intervals should also cover maximum 3-year intervals for children and adolescents, where we see the large increase in IGF-1 levels, and we do include 4,200 children in this study cohort. These are intervals which are yearly from 0 to 20 years old. In addition, we are told that we must include Tanner stages, and these must be gender specific, and these are also covered in a cohort of over 850 children where Tanner stages are provided. So sex-specific reference intervals for children aged 6 to 18 years are required by the consensus statement, and these are covered within the reference intervals published for the IGF-1 assay. So that's a really key publication to be aware of for the IGF-1 assay for the reference intervals. These are 10 recent publications, and really many clinical trials in the US and worldwide leading to the approval of new therapies in acromegaly and other growth hormone-related disorders have been approved by health authorities, which came from studies using the IDS assays. So these are some of the recent publications. So with that, I'd like to thank you for your attention, and I would be happy to take any questions in the Q&A session following this webinar. Thank you.
Thank you both for your wonderful presentations. We will now begin the Q&A session. If you have any questions for our speakers, please type them in the chat box now.